All right, we're moving on to our first new topic of the year, which is topic 3. The general name of topic 3 is thermal physics, and I'll just kind of, so here's the big name of it is, or the overall arching topic name, topic 3, is called thermal physics. And the subtopic we're going to discuss in this video is topic 3.1, which is thermal concepts. And this is going to be today's video. And then in your next reading, we'll actually cover topic 3.2, which is gas laws. And basically, we'll be applying thermal physics to the notion of gas laws. Now, our whole premise for today really relates to the IB topic. I'm going to introduce it using a different IB topic. The IB topic we're going to introduce today's idea with comes from mechanics, and specifically topic 2.4, which is work, energy, and power. And what we're saying in this topic that's relevant is our statement of the conservation of energy. And what the conservation of energy specifically says is energy is neither created nor destroyed, it only changes form. Now, that's a very vague way of saying it. Let's, of course, like we always want to do with these vague, well, they're not vague, they're very specific. It's just if you don't have experience doing physics, and of course, this is your second year doing physics and we're introducing new topics, this can seem kind of like a nebulous statement. So let's make this a little bit more practical. This statement of conservation of energy brings us to the big ideas of this video, and we've got two of them. Okay, so the first idea is well, we've got a few ideas, and I want to summarize them now. Here's the first idea: temperature is more than just how hot or cold something is. Okay, so that's like our gut feeling definition of temperature usually. The second thing is temperature and heat are two very different but related ideas. I won't say related, I'm going to say connected. And then here is the thing that actually comes from this IB statement of the conservation of energy. So this is our old conservation of energy law, which is fine. You know, it's a nice law to know. We want it memorized for our paper 2 questions, etc., etc. But this is how specifically this law relates to what we're doing today. So everything about today is the idea that heat is a form of energy. That is the big idea for today. That heat is a form of energy. This is such an important thing, I'm even going to make it bold. So that is our huge idea for today. And all we're going to be doing is simply starting with this idea that heat is a form of energy. We're going to lay out some clear definitions of what is temperature, what is heat, what happens when a hot object touches a cold object, and how does energy move from one object to another when we're talking about transfer of heat, like what's going on there, and what are some things we need to be careful of. So to this end, we're going to just jump in and get some simple definitions and ideas out of the way. So first, okay, first idea that I just want to get out of the way is our real definition of temperature comes from experience. Okay. We say hotter, and again, this is really vague, right? What do we mean by hotter? Well, we'll get to that in a second. We say hotter objects have higher temperature and cooler objects have lower temperature. And so instead of defining temperature directly, what we actually do is we come up with a notion of what we call thermal equilibrium. So we just take this observation. We observe that hotter objects touch cooler objects, and the hotter object cools down, and the cooler object heats up. What we do is simply turn this into a statement that we all agree to because we've never seen it contradicted. Now, some of you might say, well, I've seen it contradicted. I can put something in a refrigerator and then I can see I can actually, put coldness into things that shouldn't normally be cold, blah, 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 that kind of a thing. Or I can remove heat from things and or, things like that. But we're not talking about machines. That's a very special type of situation we're going to get to later on. We're talking about like when you just leave things out in the real world without any kind of machinery or anything like that. We're just saying the natural tendency of a hot and a cold object stuck together is that the hot object gets cooler and the cooler object gets warmer. And so we just agree to this. And so what we do is we come up with two definitions, okay? So we just assume, so in the past, we just called hotness heat. We called this, I know that's circular, we called this sense of being hotter, well, heat. And we simply said that two objects have the same temperature if they don't exchange heat. And we simply call this thermal equilibrium. Okay. Then what we basically say is we can go back to this older definition and simply say if objects are not in thermal equilibrium, they will exchange heat. And finally, on this notion of temperature, in the 1800s, after some experiments, this weird thing called hotness and coolness was discovered to be a type of energy. Okay, and we'll do some labs on this to show this. Okay, so what we're going to basically say, we're going to clean this definition up just a little bit more. So what we want to know for IB, okay, first, we're going to say heat is a form of energy that gets exchanged on a molecular level. Okay. Temperature is a measure of thermal equilibrium. If objects are at the same temperature, they won't exchange heat. If objects are at different temperatures, heat energy goes from the higher temperature object to the lower temperature object. That's the statement of it. And now we're going to actually talk about there is a relationship between the amount of heat an object absorbs and the amount its temperature changes. So what I want to do is actually get clear, because I don't know if IB books and websites say this clearly, so I want to be really clear on this. Okay, and I'll say it like this. Okay, I'll say it like this. There is a formula that explains how much the temperature of something goes up when you dump heat energy into it. So I want to be really clear. So here's what I mean. Okay, I can dump 10 joules into say a gram of oh my gosh, I'm gonna make up 1 gram of one substance. Sorry, I'm tired. I can dump 10 joules into 1 gram of one substance, and its temperature might go up 2 degrees, and I dump 10 joules of energy into another substance that is also 1 gram, and its temperature goes up 10 degrees. Okay, how do we calculate what's going on? So the formula we use in IB physics looks like this. The formula is Q equals MC delta T. And let's get some units down. So this is heat measured in joules because it is energy. Like every other energy, it's measured in joules. Change in temperature, well, that means we have a temperature change. And to be clear, in IB physics, we measure temperature in Kelvin. And that's actually the, so we measure temperature in Kelvin, and that's going to be Celsius plus 273.15, just so you know. M is the mass, and we actually measure it in kilograms, if I have this right, or we measure it in grams. Okay, be careful. And then C is called, this is the important one, this is called the specific heat capacity. And this is the thing, this tells you how much the temperature of something goes up when you add heat to it. Okay, it's either given or you're calculating it. And what we're going to be doing in class is focusing on, okay, here's the formula. We're going to burn some Cheetos. We're going to do some calculations with ice and water. I'm going to actually have you do some calorimetry with this to actually calculate in the real world what's going on with this letter C to understand it better. Okay, that's one way in which heat does things. Heat. You dump heat into something, it absorbs that energy, and the temperature changes. Depending on what the object is, the temperature change may happen by different amounts. Okay, the next idea, okay, more IB stuff, okay. So what we'll say is this, okay. When you freeze/melt, or vaporize/condense So that goes from the liquid gas transition or the solid liquid transition. Something. This takes heat, and this heat doesn't change the temperature of the object. Okay. So the formula for the amount of heat it takes to melt something is given by Q equals M times L. And I'm going to write another formula here and explain it in a second. We have the heat of what we call fusion, and then we have the heat of what we call vaporization right here. So, and then the amount of heat it takes to vaporize or condense something is given by this formula here. So these two formulas aren't about temperature change. They're about, all right, I've got some ice at 0 degrees Celsius. I'm going to melt it. How much energy does that take? So I've got 10 grams of ice at 0 degrees. If I melt it, the temperature won't change. It'll just turn into a puddle, and I want to know how much energy that takes. And this thing here is called the latent heat of vaporization. Again, it's given, and this is called the latent heat of fusion. And what we're going to be doing in class basically is we're going to be taking our energy ideas, applying it to heat, and basically saying, all right, we're going to be basically spending all our time in IB physics in this, like what will we be doing calculation-wise and paper-wise? We're going to be doing a couple things. So what are we actually doing with this? Number one, we're going to use heat to get final temperatures when we mix things at 2 different temperatures. And I'll be showing you how to do that in class with the formulas. And then the next thing we'll be doing is we will be calculating how much heat it takes to melt / freeze or boil / condense something. And when we say heat, of course, we mean energy. So that's where we're going with our calculations in class. So when we come to class, we're going to review all these ideas, of course. We'll do a bit of lab work, and then we're actually going to go ahead and look at IB-style problems to do this. So I hope this introductory video was a little bit helpful. Go ahead and do the reading now, and I think this little video will kind of preload some ideas and help the reading make a little bit more sense.